As a leading supplier of such training systems, we have equipped roughly 10,000 institutions worldwide with hydrogen fuel cells and with renewable energy technologies in 65 countries. Here, just an overview of some universities using our systems. We manufacture training systems. We have an industrial backbone. We manufacture also fuel cells, industrial fuel cells, and we execute projects together with the universities. As you may know, the electrical demand worldwide is still increasing, especially in developing nations. And if we look how much fossil fuels we have been consuming in the past, the numbers are horrifying, and the tendency is still increasing numbers of fossil fuels being burned. And at the same time, we are facing global warming. So what we do in Germany is we are implementing more and more renewable energy technologies in our national grid. And to date, believe it or not, 25% of our national electricity is coming from renewable energies already, which covers roughly 20 million people with electricity. And as a positive side effect, 450,000 new jobs have been created in this field. So nearly 500,000 Germans now work in the field of renewable energies. Our target is to increase this number to 80% in the next 20 years. However, already today we are facing a big problem. The challenge is that we have an overproduction of renewable energy during peak hours, meaning 11 o'clock in the morning, noontime, 1 o'clock, 2 o'clock in the afternoon. As you can see here, we have an overcapacity of 30%, and this means we have to disconnect some of our windmills on our photovoltaics. Otherwise, this overcapacity would destroy our network, and this is crazy. I mean, today we have 25% coverage of renewable energy. When everything is at full swing, we have to disconnect it. Otherwise, it will damage our grid. This slide shows this very, very clearly. This over and under supply of renewable energy. You can see here the curves at the bottom. This is the load of a typical German city between midnight, noon, and again midnight. You can see here in blue, this is the yield of photovoltaic power in this city, and you can see that in the morning hours, the load cannot be supplied by renewable energy. The load after, let's say 8, 9 o'clock, will be supplied by photovoltaics, and in the evening, then again, it cannot be supplied. At the same time, we see very clearly the oversupply here. And there, whatever you see in blue color, this is a surplus of photovoltaic energy which cannot be used, and the idea is to harvest this surplus of energy and to save it and finally use it to cover the load in the evening hours and nighttime. And this could be done with hydrogen, a fuel which is environmental friendly. We can create a fuel by splitting water from the surplus of solar and wind energy, electrolyze water, we create oxygen, which we release to the atmosphere, we store the hydrogen, and then later on in a fuel cell we can reconvert this hydrogen into electricity, and the only byproduct again would be water again. What sounds like science fiction to you will become reality in our new Berlin International Airport. We're just building it. It will be ready hopefully in October next year. And here we will have wind park, solar, hydrogen storage, hydrogen generator storage. Total, a French oil company, will operate filling station for cars, for buses, The German government is seriously investigating how we can store huge amounts of hydrogen in our caves and mines. We have a lot of caves from salt mining and coal mining. And some of you may ask yourself now, what is a fuel cell? Well, a fuel cell is an electrochemical energy converter which converts hydrogen and oxygen directly in an electrochemical process into DC electricity, heat, and the only byproduct is water. So it's a very clean technology. In the center of this technology is a membrane. This is a polytetrafluoroethylene membrane with sulfonic acid change. And this membrane here in green is permeable for protons. This is why we are calling it a PEM fuel cell, proton exchange membrane fuel cell. We have a catalyst here in gray on both sides of the membrane. If hydrogen streams in, then the catalyst removes an electron from the hydrogen, another electron is removed, finally protons are formed. The protons can migrate to this side, whereas the electrons stay on the left side. After a while, we have a lot of electrons on the left side and a significant amount of protons on the right side. It means a charge separation, minus here on the left and plus on the right side. Charge separation means voltage, and voltage means we can drive electrons through a load to the other side, where on a catalytic surface the electrons are transferred to oxygen and O2 minus ions are formed. These O2 minus ions catch the protons under the formation of water, and that's the end of the story. As long as you have hydrogen available and air or oxygen available on the other side, the system delivers electricity in an endless way without any movable parts, without any mechanics. It's a very smart system. One of the advantages of this technology is that the very high electrical efficiency, 50% efficiency compared to the conventional way of burning a fuel first, creating heat, then mechanical movement in a steam turbine, and then electricity. We all know that we are limited by Carnot's process to 25%. So this is quite a difference. Many people say, why don't we use batteries to store electricity? Batteries have an intrinsic disadvantage, because in a battery you always have the converter and the fuel mixed in one block. Whereas in a fuel cell system you can separate the converter from the fuel, and if you want to increase the capacity of your storage, then it is very easy just to add more fuel to the system. Let me give you an example. Let us assume we have a car which runs with a battery, and this battery is good enough to run this car for 1 hour. And if we want to go for 2 or 4 hours, then we have to add 2 or 4 more batteries to our car, which is a big burden for the car, because its batteries are big, bulky, and especially heavy. If we run a fuel cell powered car, we can just increase the number of fuel. We just add more fuel into our tank. And if we now compare the amount of fuel, hydrogen, as you know, is very lightweight. If we compare the weight or the volume of the hydrogen added to the addition of lithium-ion battery or a lead-acid battery, you can see that weight-wise, but also volume-wise, fuel cell technology has a big advantage, and this is why it is now adopted by the automotive industry. One single fuel cell delivers an ideal cell voltage of 1.23 volts, but because of catalytic losses and ohmic losses, the usable voltage of a fuel cell is 0.6 to 0.9 volts only. And you may think this is not too much, so what can we do with those 0.6 to 0.9 volts? But what we can do is we can connect several fuel cells in series. Not like this, but we are stacking them up like a book. We can put as many fuel cells as we want together in a so-called fuel cell stack. We are separating them by so-called bipolar plates, here in gray, a graphite plate which acts as an anode on one side and as a cathode on the other side, and then we are putting together a bipolar plate, fuel cell, bipolar plate, fuel cell, bipolar plate, fuel cell, and so on. And the number of fuel cells combined in such a stack in the end determines our voltage. 100 of them deliver a voltage of 60 to 90 volts already, and the size of the plate determines our current, and both voltage and current determines our power. This is a typical 1 kilowatt fuel cell. Just imagine the size is about as big as a package of toast bread, and this fuel cell stack as such is not yet operational. We have to add additional components to make it on the long term operational, meaning we have to add an air compressor. We need to press in air all the time to that fuel cell, because the cathode side needs always fresh oxygen, and this is coming from the air. We need a cooling system, an air cooling system or a liquid cooling system, which has to be added. We need valves and controller for the temperature, the voltage, the current, and usually these auxiliary components I mentioned are built around the fuel cell stack. You can see here the stack of a 1.2 kilowatt fuel cell. This is 40 ampere, 24 volts, and here are the auxiliary components, cooling system and so on, built around the stack, and we call this a fuel cell power module. And this fuel cell power module can now be integrated in whatever technical application you may have. Portable, stationary, mobile. Fuel cells are available from a lot of manufacturers, from as little as 5 watt to as high as 5 megawatt for a variety of applications. They have been first used by NASA in the Apollo missions, followed by the military. German submarines are entirely propelled with fuel cell technology, and the soldiers drink the waste in the night. The Americans charge their batteries in the field based on fuel cell technology. Automotive industry, I have mentioned it. Honda launched the first serial car in Japan and in California, 2009 already. So you can find these cars running in these areas. But the other big car manufacturers, they will come up with their fleet of cars. 2015, 2016, Kia, Mercedes-Benz, Renault will launch fuel cell powered car by that time. The challenge we have at the moment is filling stations. You need a network of filling stations so that the cars can be refueled. We do have filling stations at the moment in our big cities in Europe, especially in Germany, in Hamburg, Munich, Frankfurt. You will find these buses running on fuel cells already. But Germany will spend $12 billion in the next 4 years to establish a network of filling stations, and also to push this technology to a success in the end. So you will see that in 3 years you will find these technologies all over, and the good thing is it does not pollute our environment anymore. Also very interesting is to use fuel cells in vehicles which don't travel so far away from home, such as airport vehicles or forklifts and utility vehicles. Let us have a look at such a forklift. Usually this is powered with a battery. If the battery is empty, after 5 hours operation, such a forklift needs to go to a charging station, and after 10 hours only of charging, it can be reused. If you have a fuel cell powered forklift, then you can easily refill a canister within minutes, and off you go again. And this is why big warehouse operator like Amazon or Coca-Cola company, they are using now today fuel cell powered forklift. Another application about this technology is uninterruptible power supply solutions, off-grid power supply, for example for the telecom sector, server stations, repeater stations, but also hospitals, or those who need 100% energy security in case of a power disruption. If you want to build an UPS system with a 100% reliability, you can only rely on new batteries. a battery older than 1 or maximum 2 years, especially if stored in a hot environmental condition, is unpredictable. You can test it today, and you think it's working well, and in the next minute it may fail. This is why you have to, if your requirement is 100%, you have to replace batteries latest after 2 years, and buy a new battery. If you do this for 5 or 10 years, then your cost of recycling is so high that in the end the fuel cell system is more economic. And these are the sophisticated users who implement fuel cell technology already today. The mass market, this is what the experts say, will be coming by 2017, 2016, but you are preparing students already for a business life far beyond this time. A student who graduates today will work for 30 years in a technical environment, and therefore it is good to prepare them very early with these technologies. And we have various training systems. For example, our professional training system, which uses photovoltaic, an electrolyzer, a single PEM fuel cell, a resistance, load, voltage and current are displayed with course material which cover the typical lectures in physics, such as Faraday's law, Ohm's law, serial and parallel connection of power sources, how to calculate a optimum power point of a motor, and all that is covered by these courses, including how a fuel cell works, why does a piece of silicon deliver electricity from a photovoltaic cell. All that is part of the curriculum which we provide. Same for the clean energy trainer, and I think you have already procured such a trainer. It combines a wind energy here, a wind turbine, photovoltaic, a hydrogen generator, here a stack of fuel cells, 5 cells put together. The students can take it apart and reduce the stack size, connect it to a load, which also is a data logger, and then connect it to a computer. Here, the students can discover the complete energy chain from generation to conversion to storage and finally supply. One of the experiments is, for example, to put together all the sources and then apply a load to the system, for example, by switching on air conditioning, light, computer and cooking stove. And then a certain load profile is being built up, and the students then have to cover this load profile with the use of renewable energies. Very popular in physics departments in Germany, but also electrical and mechanical engineering departments are our instructor training system. This is a training system for fuel cell technology. We are using here a 50 watt fuel cell, air-cooled. It is powered up by a metal hydride canister. Metal hydride canisters are steel canisters streaming in to a so-called metal hydride. This metal hydride is solid. It doesn't contribute to the internal pressure, and therefore we can store hundreds of liters of hydrogen in such a canister without even without increasing the pressure considerably. If hydrogen is released here, it goes through a flow meter. The hydrogen flow is measured in milliliters per minute. The students can measure voltage, current. A load is on board where they can display the power generated, and finally a DC to DC converter stabilizes the output voltage and load. Here a customer load is connected in the form of a traffic light, and the typical topics covered by this system is internal resistance, parasitic load, thermodynamics of power conversion, how to determine the efficiency of a power source and to compare it to an overall system efficiency. So these are topics which you already cover in your everyday lectures, but at the same time the students can study such a fuel cell. They can find out what factors do determine in the end the performance of a fuel cell. They can increase the temperature or reduce the air supply, and then see how does these affect the performance of a fuel cell. We have a real-time display of the current data, so data monitoring is possible. The experiments can be done manually or fully automatically, as you can see here. And if you ask how can we refill this metal hydride canister, there is a hydrogen generator. It's a small table generator. You just fill in distilled water, connect it to the canister with one click, and then you plug it to a 230 volt outlet, and then automatically hydrogen is generated and refills the canister. And if you say, and a lot of German professors say, but that's not the a clean circle, we want a complete clean circle, then we can offer an extension, the solar hydrogen extension kit, with photovoltaic cells, a cabinet with all the necessary inverter and converter and a battery included, and also software included, so students can generate hydrogen as a fuel from photovoltaic power. The next, I'd like to talk in my next chapter a little bit about hybridization. Hybridization means we are combining different power sources for the sake of gaining some synergy effects. And in most of the technical applications, a fuel cell is combined with a battery via a DC-DC converter and a battery charger with a battery, and this has a lot of advantages, and I'd like to explain this to you in form of an example. Let us assume we have a pump in our garden, and we want to impress our neighbor every day at 12 o'clock noontime with a fountain which shoots out of our garden at 12 o'clock, and after 1 o'clock we say it's enough and it can finish. And next day again we want to impress him, 12 o'clock we want to operate the fountain. And if this is a 1 kilowatt pump, we can use a 1 kilowatt fuel cell to directly operate this pump and to generate this fountain. But we can also use a smaller fuel cell, a 50 watt fuel cell, which we allow to recharge a battery for 20 hours. And then we have 50 times 20, 1 kilowatt hour in that battery, and then the battery can take over and supply the pump with power. And when the pump switches off, the fuel cell has enough time to recharge this battery. So what are we gaining due to this hybridization? We gain a range extension of the battery, but also a range extension of the fuel cell. We can equalize the load distribution and therefore save synergy, overall system costs. This solution is cheaper than using a big fuel cell, and we can protect the fuel cell from overloading. If we put together a 1 kilowatt pump and a 50 watt fuel cell, this is not a good idea because you would easily damage the fuel cell. But if you put a battery in between, then the battery can take the peak load, and this is not a problem at all. In the end, a student in electrical and mechanical engineering should always consider the load profile and how does this load profile impact my power source. In this case, how does it impact my hybrid system? Well, this can easily be studied with a Nexa training system where students can dimension and balance the fuel cell size versus the battery size versus the amount of fuel stored. It is based on a 1.2 kilowatt fuel cell, a commercial fuel cell, an energy management module with all the necessary AC and DC to DC and DC to AC converter, battery charger, a load is on board, and this is, by the way, a full-fledged UPS system and an uninterruptible power supply system. You can directly take 230 volt from that system. Students will find out what are the stable conditions for operation, which fuel cell size is required, how to optimize the battery capacity versus the hydrogen capacity, and how does my hybrid system respond on a load change. So if you apply 50 watt and all over a sudden you change the load from 50 to 1000 watt, then you can monitor in real time how much current is going from my fuel cell to my DC-DC converter and how much is getting into my battery as a charge or out of my battery as a discharge. You can monitor the power of each step in real time, the efficiencies and the losses step by step. Hence, students can optimize the system parameters to optimize the full hybrid system, and this is essential for all those who want to integrate such a system one day in an own technical application. Also available a lot of experiments, a time chart with all the relevant fuel cell parameters which can be monitored, and also we put a big emphasis on battery charging because this is also something which is lacking today in the students' education. And if the students are knowledgeable about this technology, I'm sure they want to integrate this into their own projects, and we offer the same fuel cells as components which have been used for training purposes. Here, the 50 watt fuel cell from our instructor training system to be integrated in a model car or any other application you may have in mind. This 1 kilowatt or 1.2 kilowatt fuel cell from the Nexa training system can also be integrated in a boat or in a go-kart or even in a small car. That's very popular in Germany, in Turkey, even in Bahrain and Saudi Arabia. They are building such cars, and they compete with each other in the Shell Eco Marathon. Students who compete with each other who has the most energy efficient car. In Japan, fuel cell technology is very widely spread as in houses for combined heat and power. 20,000 houses, for example, in Tokyo are equipped already with such a system where the fuel cell is not only used as a power converter to create electricity, but also to create warm water, because you can use a liquid-cooled fuel cell to generate heat and extract the heat from the fuel cell. And if you consider heat and electrical power, the efficiency is roughly 100%. And this can be studied very well with the FC42 evaluation kit. We have here a fuel cell and here a cooling system and long hoses, and you can add your own thermocouples and flow meters, and then study not only the electrical but also the thermal output of such a fuel cell. And also available from Heliocentris are 4, 8, 12 and 16 kilowatt fuel cells as a module to be integrated in the laboratory if you want to study and evaluate such a system. Now coming to a more complex hybrid system, our new energy laboratory. This combines photovoltaic, wind, fuel cell technology, hydrogen storage and hydrogen generation, battery, the national grid, and energy management. This is for students who want to gain knowledge on and a practical experience in new energy management. The students can create their own autonomous hybrid system, applying all these technologies based on a 1.2 kilowatt photovoltaic system, 400 watt wind turbine, 1.2 kilowatt fuel cell. The students can freely decide whether to use the energy generated from photovoltaic and wind directly, or whether to store it in the battery bank, or whether to store it in form of hydrogen and use it later on. They can decide whether to connect the public grid or not. Challenge the system with an electronic load which is on board, but students can also bring their own load from home, AC loads and DC loads. They can freely select the energy paths of the system, and in order to get an idea which is the right way to use the system and which energy paths are useful and less useful, we need data. And we generate data from about 40 sensors, environmental data, photovoltaic data, hydrogen and fuel cell data, wind data. All this is connected and collected in a central monitoring system here, which you see here, so that the students can decide which energy paths to take and what is the right way to operate for a certain load profile given. They can use the system in 4 different ways. In a component test, students can investigate only the photovoltaic, or only the wind turbine, or only the fuel cell independently, so that they get an idea on how the single components contribute by itself to the overall system performance. They can use it as an island grid. If they put this switch on island grid mode, they disconnect the system from the public grid, and then they have to be very careful in how to monitor what is the intake in photovoltaic and wind power at the moment, how much have I stored in form of in my battery and in form of hydrogen, and which load can I apply for how long. If they don't do that properly, then the system will collapse, and this is what happens so often all over the world. It's a very realistic scenario. In the UPS mode, the students can investigate how such a hybrid system takes over the load in case of a power disruption. And with one mouse click, the students can disrupt the power and disconnect the system from the national grid, and then see how such a complex hybrid system immediately takes over the load with a high reliability. And finally, in a grid backup mode, the new energy is our main power supply. We want to use as much as we can solar and wind, the energy we have stored in the battery and in form of hydrogen, and only in case this is not enough, the grid is periodically kicking some energy in so that the system does not collapse. And this last scenario has been executed in several projects in Germany and in the Middle East, and one very nice one was in Bahrain, where we established it, connected it to a house. The house is entirely covered with renewable energy. We have here a wind turbine, photovoltaic, fuel cell, a battery bank. This is an island grid where the house is connected. The public grid is used as a backup. This is how the system looks inside. It combines all relevant new energy technologies, energy storage technologies with conventional technologies. This is the house, Dar Nakhil in Bahrain, which acts as a load. We have photovoltaics and wind energy. If the surplus is automatically stored in a battery bank and in form of hydrogen here in these metal hydride canisters. And if somebody enters the house and switches on the light or the air conditioning system, then this is a load request. And then the photovoltaic and wind is carefully checked. Is it strong enough? If this is yes, automatically this energy is sent to the load. If it's still a surplus, the surplus creates is used to charge the battery and to create hydrogen. If this is not enough, if the photovoltaic and wind is not sufficient, then the battery state of charge will be checked. If the battery says yes, we can supply, then the battery will supply the load. If this is not the case, then the hydrogen tank will be checked. Can you supply hydrogen to the fuel cell? If this is yes, immediately the fuel cell gets started and provides electricity to our load, and only if this is a no, then the grid finally kicks in electricity so that people don't have to sit in the dark once the load is too high. And we have executed this project with a 1.7 kilowatt windmill, which you can see here, with a very low cutting wind speed of 3 meters per second. It means it operates even if you don't feel it on your skin. 3 meters per second is a very low wind speed. Photovoltaic 4 kilowatt, here the array which we installed, a 1.2 kilowatt fuel cell, hydrogen generator and storage canisters. A PLC is used to run the system here, all the converters, the hydrogen generators, the fuel cell is over there. This is down a hill, this house from the side. There is a public display showing all the relevant parameters to the public, so the data are flying in and out of that system, such as voltages, currents, power generated, carbon dioxide saved, carbon dioxide saving since installation, and many more. We have a large indoor display showing all the relevant data, whether it is battery data or wind data or solar data or fuel cell data, environmental data. More than 60 sensors are installed in that system, and this is web-based. It means it is connected to the internet, and you can use this monitor and multiply it and hang it in different departments so that all over your university you have information on what's going on the campus. You can also log in from your desktop in your office to that system, and if you open it to the public, even Egypt-wise, scientists can have access to such a system. Whoever has access to that website in the end can tell the system, log the data for me every second for 1 year, or every 10th of a second for 1 month, and then you can utilize the data, intercorrelate them for scientific purposes. This is ideal for prototyping and for doing some research, especially if you want to implement a green building one day, or if you want to establish a building with renewable energy technologies one day. This is how the system looks like in Bahrain. We have installed everything to the ground in Saudi Arabia, in King Saud University in Riyadh. They asked us to install everything on the rooftop. That's just an idea that also rooftop installation is possible. We can provide a complete center of excellence using a basic lab for renewable energy, a complete fuel cell laboratory, plus a new energy lab for energy management, and a new energy power supply all together. And the advantages are that you have a full energy mix. All relevant energy systems are combined together. Students get awareness on energy storage and energy management. These are the two hot topics and the biggest problems with renewable energy today. It is an innovative concept and will create publicity when you install such a system. You can prove that you are providing state-of-the-art equipment to these students, and the energy awareness amongst your students all over the campus. Small movies about the new energy laboratory, the educational one, and also the new energy power supply system, the one in Bahrain. But we are running a little short of time, so I would say let us do the question and answer first.
The one in Bahrain.
Only the one in Bahrain. Okay, then I'll quickly show the one in Bahrain.
We in BAPCO are very conscious about the environment. So far we have talked about photovoltaic cells, which produce energy, and the generator, which is using the wind energy to produce power. And there is a third type of electricity generator, which is using hydrogen. Can you please explain to me, if we stand on this side a little bit? And we talk about how the fuel cell is working.
So first, to make the fuel cell run, we need hydrogen, and this hydrogen is produced also by the same sources as talked before, from the solar cells and from the wind turbine, and then it's converted down here in these two machines. These are hydrogen generators using electrical energy and water, which is split up into hydrogen and oxygen. And then the hydrogen goes up to these two panels, the hydrogen storage. So behind it, you will find the storage canisters. It's like small cylinders, 6 pieces in total. You have some pressure indicators here. At the moment, they are just being charged. And then it comes when the energy is needed during the nighttime. It goes back to the fuel cell. This is this part in the middle. And this is the reverse.
The hydrogen from this storage.
Right, it goes back to the fuel cell, and then develop the reverse process to the hydrogen generation. It's the fuel cell uses the hydrogen and the oxygen to produce electricity and to power the building again.
And the byproduct of it is the water.
Right.
That's
That's about the same way as the hydrogen was made. You put water in, and you get the hydrogen out. Now we put the hydrogen in, and you get water and electricity out.
And this room becomes very rich with oxygen. So this is the healthiest place to be in when you are tired or when you have good asthma, because there is a rich oxygen atmosphere and it is the nicest place to live in. Beautiful oxygen. We wanted to also mention that during this photography session, the total lighting system has been powered up by the energy lab, which has been installed at Dar al-Nakhil.
Before we open the floor for questions, I know that some of you have commitment and they have to run, but Dr. Claus Fischer will be with us for the coming hour in the physics department for anyone who would like to stay longer. I would like to say thank you very much, Dr. Muhammad. Thank you very much for being here. There is an international, the largest exhibition for hydrogen and fuel cells in Hanover, April 8th till the 12th. For those who would be interested after this very interesting lecture to really go beyond this type of questions.
Thank you for the presentation. Actually, we'd like to invite you to come and see our lab. You mentioned some departments. We are the Department of Petroleum and Energy Engineering.
Yes.
We have a renewable energy lab, and some of these units we have in our lab.
Okay.
I have a serious problem with what you said. This is really a sales presentation with no technicalities whatsoever. You are in a university, and we have the same thing in the lab. And you mentioned fuel cell very casually. There is more than just PEM fuel cells. Mm-hmm. And I think it is important to allude to this. And then the problems related to PEM fuel cells in terms of the protonic membrane, whether it's Nepean or whatever, the degradation, the possible degradation of the membrane, the bipolar plates and their problems, the microstructure of these bipolar plates, the nanotechnology, which is the emerging technology in the industry. Although you're very biased towards the PEM fuel cells, I'm personally biased towards the SOFC, which is the solid oxide fuel cells, and I think a part of your demonstration should show a comparison between the different fuel cells and their applications.
In a long presentation, I do that.
Yeah, but your focus is simply, on a product that simply shows you to push button and get a result. In a university, you need a little bit more than that. We have these systems, and if I want as a matter of fact, we have a course in our department that precisely says that, hydrogen fuel cell. This is a course that I teach, actually. Again, I want to show my students what a PEM fuel cell is all about. What are the components? As a matter of fact, we even sent a letter to the manufacturer telling us, because it's no secret anymore, you know, the components are very well known. If I change the membrane in a fuel cell, what type of efficiency do I get? What is the cost per kilowatt? You know, these are figures that are very important. If I can reduce the operating temperature of PEM, this will, how degradation problems affect the cell performance. How do you compare this to the solid oxide fuel cells, which is really a more reliable and more durable and more promising in the long run compared to PEM. But anyway, we can discuss this later, but I'd very much like to visit our lab with your Egyptian.
As soon as we finish, I think we did.
Yep.
Any other questions? Thank you for coming.